Hello everyone, my name is Shijun from Central South University. I am honored to be here at ASE to share this research. The name of our work is Industry Practice of Directed Kernel Fuzzing for Open Source Linux Distribution. In this session, I will first introduce directed kernel fuzzing and the motivation behind our research. Then, I will discuss the challenges in practice within the open anonymous community and the corresponding solutions and our evaluation results. Directed kernel fuzzing is an automatic testing method that operates in virtualized or emulated environments. It utilizes specific system call sequence to focus on particular code segments. Key strategies include distance-guided exploration and invalid input pruning. State-of-the-art tools in this field include sysdirector, DLLF, Gravy. For the motivation, customized Linux testing focuses more on specific features developed by the community. For the example, since 2020, the Open Anonymous community has actively engaged in IOU ring submodule development, contributing numerous features and optimizations. Moreover, directed kernel fuzzing are not used in real workflows within Linux distribution. So, for our industry partners, they also want to find more bugs by fuzzing and follow up the academic work. So, we deploy 4 directed fuzzers, including sysdirector, Gravy, DLLF, syscaller with code filter, on Linux distribution kernels. The directed kernel fuzzing procedure is presented in figure. In concrete, it includes 4 steps: target localization, input preparation, directed fuzzing execution, and crashes analyzed. And we, based on community's requirements, fuzzing for specific modules of Linux distribution, including anonymous kernel 5.5 and 6.6. This table illustrates the challenges and solutions in each stage of the fuzzing process. The first challenge is the target-related kernel configuration are disabled. Continuous kernel fuzzing typically utilizes the predefined configuration template to compile kernel. However, this approach presents certain difficulties. For example, when we attempt to test the patch for temporal file of schedule, it's necessary to analyze the configuration option dependencies in config of net, kconfig of schedule, makefile of net to enable. However, manually enabling the required configuration settings from the patch is impractical. Our solution is utilized krepair to specific configuration options for continuous fuzzing. In detail, krepair is an open source tool implemented in Python, designed to optimize Linux kernel configuration files to achieve nearly complete patch coverage while maintaining fast build times. We implemented an automated script in continuous fuzzing that helps to turn on patch-related configuration options based on existing template with minimal computational resource. The second challenge is the fuzzing corpus. Firstly, existing directed fuzzers utilize its custom descriptive language called syslang to generate system calls as input for the kernel. Current fuzzing framework primarily utilize extensive cropper to improve code coverage. However, it may result that unrelated initial seeds limit fuzzing performance. Then, due to community-specific requirements, different Linux distribution features are distinct from the mainstream kernel. It's typically configured through specific interface in syscontrol or proc file systems. We must have an effective way to fuzzing interface. For challenge 2.1, during enterprise fuzzing, we collect coverage information for each executed syslog, including covered basic blocks and their respective address. Whenever a fuzzer discovers a new valuable syslog and integrates it into corpus, we store the coverage information. Before each directed fuzzing, we filter seeds based on positional information of target points, discarding ineffective syslog that cannot reach the target code. For challenge 2.2, we developed a script for generating system call template for fuzzing features specific interface. The process is straightforward. First, the user provides the test interface information for syslog generation. Next, this information is passed to determine the absolute path of the interface. Finally, using our predefined syslog template, the tool automatically generates sets of syslog calls. The third challenge is the independent fuzzer. Execution limits fuzzing effectiveness. As illustrated in the table, difference in application scenarios and testing requirements lead to diverse input. It's worth noting that feature testing from an open source community's perspective typically refers to a specific function introduced in a release of Linux distribution. In addition, when a requirement matches the testing scenarios of different fuzzers, the intuitive approach is to choose the tool with better results and specialize in directed fuzzing to improve testing efficiency. However, different fuzzers in practice have different advantages due to their inconsistent implementation. To address this challenge, we designed a scheduling method based on applicability of different directed fuzzers. We first analyze the form of test inputs, thereby scheduling suitable fuzzers. Then, we utilize control flow relationships between files to represent features and use a unified format for fuzzer input. When scheduling different tools that meet the same testing requirements, we utilize setup to link these tools to share the seed coverage. The fourth challenge is much manual work to triage and analyze crash. When Linux distribution kernels encounter crashes, communities need to conduct an analysis to identify the type and the root cause. This analysis typically includes evaluating the impact, determining whether the problems arise from customized feature. For this challenge, we have designed a bug prioritization and resolution for open source community. First, we start with stability testing to see if the bug shows up consistently in the current version. If it doesn't, we consider it a lower priority issue. Next, we do community version testing to check if the bug appears in the same version of community Linux distribution. If it does, that usually means the problem comes from the community kernel, which is also considered lower priority. Finally, we look at historical community version testing. If the bug doesn't show up in the current version but doesn't in older versions, we take fix from those older versions and apply them to current one. The final challenge is the complexity of continuous directed kernel fuzzing. It's quite common for industry users to adapt the continuous testing, and we need to integrate fuzzing in the current kernel testing framework. Otherwise, the absence of continuous fuzzing may reduce the acceptance of fuzzing in practice. To address this challenge, we developed a continuous framework. In this figure, the framework includes a statistic bus, workflow, and fuzzing resource. With these modules, directed kernel fuzzing can be integrated into the current enterprise testing framework, and developers can use fuzzing to find and fix more bugs more easily. After overcoming these challenges, we conducted a 48-hour test on 4 target modules. In figure, directed kernel fuzzing achieved higher coverage rates compared to coverage-guided fuzzing, with 17.4% improvement. For bug comparison, we found 11 new bugs and reported to the developers. Table presents the comparison of bug discovery between directed fuzzing and coverage-guided fuzzing. We can see directed fuzzing have 16% improvement of bug relevance. At the end, I want to share some lessons learned during practice. First of all, artificial intelligence can be used to improve the effectiveness of directed kernel fuzzing. Then, bridging the gap between academic and industry applications of directed kernel fuzzing is important. And third, integration of directed kernel fuzzing into the current testing workflow will be necessary. Thank you for all.